All right. So what I will talk today is searching for extraterrestrial life. Okay, why should we look for them and what we have found and what kind of things we do to find them and why should we look for them? Okay. So with that, we start with first slide. So we know our Earth is full with intelligent life forms. Like you can see a lot of students at a university, like you are also students. You are part of them. But sitting in Bangladesh doesn't matter where you're located. All of you are very smart, and so all human beings are in general are very smart, the most intelligent life forms. We also have on this earth a lot of all kinds of animals. They are also quite intelligent. And we also all kinds of microbes. They are also intelligent because they know how to survive everything. So everything we know, they all exist in one place on the earth. Okay, so question is Earth unique or are we unique to the whole universe? Only we exist, no other intelligence being exists in the universe is a question. So let's see what we are part of this universe. The sun is our star and it is the source of our energy. So our life depends on the solar power or solar energy. And it has 8 planets, 4 are solid, and these are gaseous, but our planet is this third one, the Earth. So it's one of the planet of the sun that is our home, okay? And then our sun is not only, a system with a bunch of planets. It is extended over in a long distance. So if this is sun, the planets are around here. It's just a planetary region. Okay, this is planets. Beyond it, we have Kuiper belt, like we have no comments going extra, those dwarf planets, etc. Then we also have a Oort cloud, these frozen materials outside, largely water and the dust. So where, the comets form. So this is the huge, so as a system, you can see sun is small part, but it has, extension is very big, gravitationally. Beyond it, solar gravity is, you can say, almost zero. You can never have completely zero. And here, it has a magnetic field. It also ceases around here. Okay. So this is our sun. And we always studied the space and we sent a probe. The first probe that went beyond the largest distance is called Voyager 1. And so it traveled for about 30 years. After that, it took a picture. In the whole picture, the whole space, there's a tiny dot. This is our home, the Earth. So this picture become famous. So whenever you see it, you should recognize it. And it's called the pale blue dot. The pale blue dot is our Earth. Okay. And so this is our home. And so we occupy a very, very tiny spot in the whole space in the solar system. So we, logically said, we cannot be unique. All right. And so if this project travels and at this year or sometime soon, it will go to this place. Heliosphere means, where we have this boundary of Kuiper belt and the Oort cloud here. And then it says it will take another 300 years, to cross it. And it will take 40,000 years to go to the next star. So you can see that stars are so far apart. You already know it, but I'm just explaining, we are so far apart. And sun is just one of them, one of the stars, one of the star in our own galaxy, Milky Way. So Milky Way has about 200 to 400 billion stars. We are just one, we have just one star, sun somewhere near the edge, right? So there's nothing particular or specialty about us. And most of the star, about 99% of the star, they have similar kind of lifetime or life form like the sun. If so, if we are in the sun, in our star going around, so chances that, there may be other stars which can also have intelligence beings going around, right? Okay, and this is the universe. So this picture shows 43,000 galaxies like our own Milky Way. They are actually real galaxies with the picture. All the light you see, they represent the temperature, light coming out, distance stretching, all parameters together, put into this model. And this is, you can say, universe. And so we are just one dot in our galaxy. And in our galaxy, we are even almost on a tiny, tiny dot. But it is not, our universe is not only 43,000 galaxies. Our universe has about 2 trillion galaxies. So if the universe is so vast and so much many galaxies and stars, that means there's a high probability that there'll be life forms in other places too. Okay, so the life form, it can be very primitive or it can be very advanced, intelligent like us. The primitive is, it could be something similar to what happened to our Earth. When this is a 3-cell animal life form, it is called trichoplax. Okay, so this is the first trichoplax, and it existed in the water in 550 million years ago. But it was, well, I don't know, it is highly intelligent. I think I copied it from somewhere. But it doesn't have mouth, stomach, muscle, anything. But it is a living form. It could survive. And we are on the opposite side, right? But how we consist of that also very important. If we want to find something living, what are they made of? So in the whole universe, all the particles are scattered. Most of the things that we know made of are made of from all those particles, including us. This is a cartoon of human being. So human beings actually are made of from the dust of the space, the scattered dust. That dust has carbon, nitrogen, oxygen, hydrogen, iron, silicon, all those materials. So all together we are made of. If we are made of from stardust, then other life forms should be made of from stardust too. Okay, so this is that's why whenever we watch aliens in the movies, so we assume that they could be similar to us, not exactly, but they also have their own language, own form, own way of living, but something similar because we are all made from the same space. So, but how do we communicate? How do you go there? It is important to communicate and go there to expand our knowledge for our survivability. But distances are so huge. And, as I said, our nearest star takes, the light from that nearest star takes about 40 years to reach our star, the sun. So they are so far apart that, like in the Star Trek or other scientific movies you see, we have to have some kind of vehicle which has warps. We say warp 1, 2, 3. You heard those words, right, in the movies? It's like, it is going at so fast, and I squeeze the space, expand there, so it's going at very high speed, higher than the speed of light, and we know nothing can go beyond the speed of light. But we can think, there may be some process we can travel at higher speed. Not only that, you also heard these words, wormholes. That means they're so far away, and then we have space and time curve. There may be some way, there's a wormhole is the shortest distance so that we can just go through it quickly. Okay, so then we can reach other places. So we have been searching for life form for a very long time. And at one point, US and Soviet Union, at that time it used to be called Soviet Union, came together and set up this observatory, you can say SETI, Search for Extraterrestrial Life Form or Intelligence. Okay, so this set is in California in 1984. So you can say that you are not born even at that time. So not me, I was born. So at that time, so we've been searching for life for a very, very long time. But so far, we haven't detected anything outside our solar system on Earth. But it has a lot of data through the years. It collected a lot of data, the signals, and the signals have to be consistent, not noise. So it will be consistent noise, so we can find out something, some meaningful message from it, saying that the message came from some other intelligent beings. Okay, but all those messages have been saved, and we expect to get something in the future. All right. So we got very excited twice. Once, we found a rock on the earth which did not belong to our earth, because we know what earth is composed of. So if something comes from outside, if we analyze that, and I'll tell you how to analyze that, we can tell that that object belongs to the earth or not. So they did not belong to the earth because it showed some kind of called basalt rock, which is created from the volcanic eruption on the Mars. So we found this and very much excited. And when it analyzed, it found carbon. It seemed like they are carbon fossils. So when we know that living forms, like even the microbes, when they die, they become fossil. So, and so it was a big news, a fossil has been found. Then it turned out that it may not be microbe, it may be, maybe this stone formed on Mars, maybe the carbon layer or the water was going down somehow, a fossil-like formation created inside, and eventually it got scattered and came to Earth and we detected it. So it doesn't confirm that even a microbe, the tiniest form of living form, exists outside our Earth. Then there was another excitement not that long ago, about 5 years ago. It says the Venus, which the second planet in our solar system. The Venus spectrum, I'll tell you, spectrum means when the light comes out from an object, and if we study that light and get information, that is called spectroscopy. Keep this word in your head. Spectroscopy is the method to get information of various objects, particularly objects outside the Earth. And those spectroscopy is done through the photons or the light. Photons are the unit of light. Yeah. So what happened, they say this signal correspond to phosphine. Phosphine is, from living form. And so there are a lot of excitement. Then the question came, in the atmosphere, how did that phosphine form? So there's some life form. There cannot be life form because Venus is very hot. It's 900 degrees Kelvin. Not only that, it's toxic. It is sulfuric acid. No living form can exist on the surface of Venus. But if you have some microbes, then the microbes probably exist on the surface. Well, it needs somehow to survive, but then there are a lot of study on it. They found that it was not accurate. The paper was not probably accurate or is the real one. Anyway, so we have been searching, and this for life form, so not a life form, because we want to know other life forms, and there is also issue, what will happen in our future when our son will die. We have to find another home. We cannot stay on the earth. It may happen, after some billion years, but we have to have technology to go to some other planet so our generations, the human race, can survive. So we have been trying to find also exoplanets, the planets that belong to other stars. The planets, belong to sun, we call planets, but if they belong to other stars, we call them exoplanets. So we have, particularly Kepler. There are a bunch of those. Kepler is well known because it detected the maximum number of exoplanets. Okay, also there's a new one which is also detecting, it's called TESS. So you can see, these are all the, you can see the dots, and all the dots, like exoplanets. That means that star system has exoplanets. This is old number, 5,800 confirmed. Now we have crossed 6,000. So we have detected 6,000 confirmed exoplanets from various stars. Okay, and these are like a classifying what kind of stars, because we want to know the classification. Not all the planets are habitable. Like gaseous planet is not habitable for us. We need a rocky surface. We can, walk. We need oxygen. We need water. And also we don't want to be too close to the star, because all the stars emit a lot of radiation which are harmful for us. So we want to stay a little bit away from, some planet which is not too close to the star. So that's the classification, and we do look for habitable one. Okay. How do we, the stars have light coming out, and we detect the light, and we study and through spectroscopy, okay, get information. But the planets, they don't emit light. How do you study the, how do you detect them? Or how do you find, is there's a living form there? So how do you detect? We detect through the light passing through it. So this is an exoplanet, and this is that belongs to this star. Okay. So it goes around it. When it is going around it, so say we have a telescope point at this position, for example. So it is as a bright, you see, always bright. Suddenly there's a dip, less brightness, because the planet is passing through it. When it's passing through it, the light from the star is passing through the atmosphere of this planet. As it is passing through there, so it is giving out photons of the atmosphere. And see, these photons are now, they have less light, but we know the wavelength range, the photons coming out. And from that, we can find out what kind of atmosphere it has. So it is not very easy, but we can still work with it and improve our instrument and find out the components or constituents of the atmosphere. And also, sometimes we cannot detect the star because planets, because the star itself is very bright. So this was the NASA devised a method technique, just block the star. So this is also one way they did it. Block the star so that the light cannot disturb. And we also found planets. The way they use star is this one, and planets are called stars with number B. A means the star. Planet B, planet C, planets D, etc. Okay. So one purpose is to study to habitable planet. So this is the fate of our sun. Our sun is 4.5 billion years old. It will survive another 6-7 billion years. But up to this, our technology has not developed so much that we can even travel to another star. So we need to work. And all the people you're sitting listening to me in that classroom, you have to do a lot of work, right? You have to do a lot of thinking. All those ideas should come to your head. Okay. What will happen to our sun? It has a lot of hydrogen. Hydrogen is the fuel. for any star. So when hydrogen, they fuse together, give out light, and that light emission, it comes out of the star, and that's what we see. But when all the hydrogen will be used up, then things will collapse, then our sun will become a red giant. You probably already know from your other sessions. So red giant is much, much bigger than our sun. So this is the like relative size. So when it will become red giant, it will engulf everything, including our Earth. So there's no way we can survive. So we need to find another home, a habitable one. Okay, so this shows the first detection of this planet, like exoplanet. And to me, it is one of the most beautiful picture I have seen. See, this is the star in 2004, I think. Yes, in 2004, it is from a ground-based telescope in the South America, uh, they detected this star and its planet. So this is the direct evidence that exoplanets exist. Before that, we did not know. We assume logical that all the stars should have planets. If sun has planets, other stars should have planets, but we didn't have direct evidence. This is the first direct evidence. Now we're getting so many. You are getting even a star which has like 7 planets, or how many, I think, yeah. See, this one has even 7 planets like us. So we are detecting a lot of planets. I don't know whether you have seen this picture. Is called HR diagram. It depends on the luminosity of the star and now the temperature. You may learn it in this workshop. So these are like classification. You classify the stars, and in that classification, most of the stars in this region of temperature and brightness. So they are not KLM. They are the stars which we have found have planets which can have similar to Earth. So that means probably habitable planets will be belonging to the stars in this region. Okay. The good news. So we have found one habitable planet. Do you know where? To the closest star we have, Alpha Centauri. So this is the sun, the closest star, which still takes 4 years for the light to reach us. This is actually, we used to think it's just one star, but it turned out it is not one star. There are 2 stars, binary stars, but they have a planet. And this planet is habitable planet. It has rocky surface. So this will be our first choice to go after 7 billion years. But first, at this now technology, if we have started, everything going there, it will take 18,000 years to reach there. And that means we cannot survive, and we cannot have so much food, production, everything travel there, 18,000. So we have to develop that technology. Who will do that technology? You will do that, no? Develop those technology. You have to think about all of those. So we have to have that kind of technology so that we can travel fast. And there are ideas, you can have like laser propelled things. If it goes like like fraction of the speed of the light, if we can do that, then still we can make it in our lifetime. We can go there maybe 20 years, but still, that's a lifetime. We can reach there. Okay. So now, how do we know, the life form exists? To do that, we have to do the spectroscopy. Okay, and we have to know that now we go with whatever knowledge we have. We are human beings, and we thinking that other life forms also have similar kind of structure. They may look different, they may live different, but they may have similar kind of cells like us. So with that information, we go on and try to find life form. But the life form, what we cannot reach there because it's too far. What we can do, we can collect photons from various places and see those photons indicate a life form. Okay, so we will do spectroscopy of the photons we collect through the telescope. So we have telescope up in the space, we have telescope on the ground. Okay, so we can collect photons. Okay, what are these photons? How these photons are created? They carry a lot of information. So photons are created actually in the atoms here. Okay, so this is an atom, but it's a simplest version of the atom, but structure is not like this. And we know that we have protons and nucleons, and electrons are traveling around, right? Moving around. One thing about it, now you are in college right now, and soon you will study quantum mechanics. Okay, so these electrons have particular orbit. They cannot just arbitrarily go here and start rotating around the nucleus. They have particular orbit. We call them quantized because the energy is fixed. If the electron is in this orbit, energy is fixed. The quantized energy, quantized orbital, and you represent with a wave function. That is quantum mechanics. Okay, but because of that kind of quantum mechanics, we are lucky. We can study them. We can predict them. So we can have, this atom has all kinds of energies. They are all quantized, not random or continuous. So it can have energy level 1. You can say, oh, this is 13.5 Rydberg unit. That's the energy unit. It can have maybe, higher energy unit, 17. Or actually, as you go up, well, you'll know that negative sign, boundary state, free state from quantum mechanics. I'm just showing these are like higher levels. So when we excite an electron to various higher levels, they, giving some kind of energy push to it, electron will take that energy and jump to another quantized orbital, nothing in between, quantized one, and it will stay there momentarily, then it will drop down. That is the characteristics of the electrons. They cannot stay there. They would have to drop down. When they drop down, the energy has to be given out. And in terms of photons or light, so the photons come out. You excite an atom, and as they go down, they give out photon, and we get light. So that's how lights are formed. Okay, and that's how the light coming from the stars. And that's what we detect. Light photons can travel for very, very long time, billions of years. Okay, so those photons, when they come, spectroscopy means we pass them through some medium which can separate out the photons, various energy photons. That is called spectrum. And if we have an element like carbon and we pass the light through a slit, they also can be separated like lines. So these lines, notice these are lines. These are the lines we detect, and this is what we study. I have to go a little bit fast, but because I don't have too much time, I just want to mention this, keep this in your head, okay? Whatever you listen, keep this on your head. Sometime you will learn all of this, okay? And understand whatever much you can. Don't worry that I don't understand 100%. So energy, when photon comes, electron jumps from one energy to another energy. So there's a jump. It can take take a photon or emit a photon. So what we do mathematically, we represent the electron with a mathematical function, and we calculate the probability of going up and down and get the energy of that photon. So this is a quantity A, B, those are the quantities we calculate using quantum mechanics. So they are related to the photon energy and how we can detect. And those photons actually give these lines. I just showed you the lines. Now, the lines formed by the photons. So for example, this is the lines. These are lines, but these lines were created when we study the atmosphere around it. And this line, okay, you see this line, says oxygen 2. It means the photon came from oxygen to molecule. If I see here nitrous oxide here, that means the photon created by nitrous oxide. So we detect this line, and these lines are characteristics for each atomic system or molecule. So if we know them way ahead, then we can tell that this is nitrogen, this is methane, or this is ozone, or this is water. Okay, so this knowledge is coming from the spectroscopy. Keep the word in your brain, spectroscopy. The one thing is that in our DNA, there are a number of elements. Okay, you can see this is as a picture of a DNA. It has hydrogen, of course, carbon, nitrogen, oxygen. Another one, the red one, phosphorus. So our DNA has phosphorus, which we are not very much aware of it. And when in the space, we see a lot of elements, particularly we see a lot of carbon, nitrogen, oxygen. Everything is there, or other elements we find. We don't see phosphorus. Okay, so then we don't know, so we don't study phosphorus. We don't see anything, we don't study much. But phosphorus we study on the earth, we use it quite a lot. So this was detected. Is it a missing link? If we don't find phosphorus, that means there is no living form. If they are DNA-based living form. Okay, so see, this is the work from Ohio State University. So the universe, there is a project called Apogee. In this one, they try to collect photons, abundance of all kinds of elements. So we can see hydrogen, yellow, this gold color, carbon, nitrogen, and phosphorus is red color. Okay, and they are detecting all kinds of photons from the universe. They're collecting and studying which is abundant, and all this you can see they are all abundant. But phosphorus, which is in our body also, phosphorus is here, is showing. You can see phosphorus is right here. Not that many phosphorus we have detected. This color is shown here. So phosphorus is not very much abundant. Why it is not abundant? That's the question. Okay, phosphorus is just a picture of phosphorus. It glows when exposed to air, and it is very reactive. It reacts with other things, and so that is the reason we cannot detect, because it's very reactive. It goes, when with some other elements, you see, it reacts and combines something, so we are not able to detect. So maybe there are more phosphorus, but we are not able to detect them. Phosphorus is very much abundant. If we are realizing it now that maybe that's phosphorus is something we need, but it is not available in the space. Okay, so phosphorus is needed, and particularly who work in agriculture, and we have this manure, or we give food to the plant food. The phosphorus is one item that they need, plants, for their growth. So the animals, and because we have phosphorus, plants have phosphorus. They go to the ground, and they go to the plant, and this picture, it just shows the cycle, phosphorus cycle. So it is very much abundant in our earth. It is part of us. For now, we're detecting some phosphorus. This is a supernova remnant. All the stars, now they will be similar to our sun, but 1% of the star will go through supernova explosion, because you probably studied it. They are the heavy stars. When they explode, they create heavy elements. Okay, and so this is the explosion. It's a remnant. Okay, and 3 telescopes took picture of this remnant and put them together to create this image of the remnant. And we have found phosphorus existed here. So that means phosphorus is created in the space. The other one is the JWST, James Webb Space Telescope. We spent a lot of money to make this telescope and put it farthest away from the sun. All those telescopes are around us, but this is the furthest one, because we want to detect very, very weak photons. Weak photon means, those photons have been traveling for a long time, coming from very long distances. And to detect that, we cannot be disturbed by the photons coming out from the sun. So that's why it is so far away, and we use gold, plate, because gold has very high reflectivity. So that when weak photon, like touches this wood, even us, it will just absorb by our body, because it will be absorbed. But this gold can reflect it, to the telescope here, focal point, and then we can do the, what can you do? Spectroscopy of the photon and find out something about other planets far away. So one of the objective of JWST is to find the living form, whether there is any life form out there. Okay, so at least it found something. It found water in a very far galaxy. The galaxy far means we start with the Big Bang, and then everything started to go away from Big Bang, far away, right? So go back means we go toward the old time when you go, and we find galaxies, and those are the galaxies we did not know exist are being detected by this JWST. That's the telescope. And it detected in a very far galaxy water. Okay, so how do you know that this is water? It detected these points. After curving it, modeling it, we found that water molecule gives out photons, okay, when they're excited, and all kinds of photons, they are similar to this. That means the JWST detected a galaxy, very far away galaxy, which has a planet which has water. So this is a good sign. We want something, some planet which is water. Okay, so this is something we study. So this is something I'm just showing from our group. So like that one, what is the curvature? This plot, from plotted by um, from a student from our group. So he plotted it, and also we're studying. This is another planet. Before that JWST, we detected water in another exoplanet. So those are the special ones for us because there could be sign of life form there, and life form means it may be good place for us to go. So this is the spectrum that was detected, and we also in our group, the student try modeling it, and see this is what they got, this kind of structure. This was the point, actual point that was measured. Okay. So I like to also mention this spectroscopy. And the JWST, not only water, it also detected sharp lines. Sharp lines means they are also coming from the photons. Okay. And we found that oxygen, hydrogen, neon, all kinds of lines that it is detected. These photons, how do we know them? We studied them already and put them at a place so that when we see a line, we match with our knowledge. We say, okay, this is neon, this is oxygen, this is hydrogen. We did not find phosphorus. We may find, but at least now this is the one of the oldest picture that JWST found. And one thing about this particular spectrum is that these photons which have been detected have been traveling for 13.1 billion years. The universe is 13.8 billion years. That means there are some galaxy or some formed, and the photons were traveling. They traveled so long, they were not detected by anything. They are just kept on traveling for 13 billion years until JWST caught them, and we did the spectroscopy and we found these lines. So, and this showed that, the study shows that the object from where these photons came, they were created 300 million years after the Big Bang. But our idea was that this kind of atoms, like nitrogen, they form 700 million years after the Big Bang, not 300. So see that the photons are giving us information that galaxies or stars form before we could think of, where we didn't, our concept, we are getting new knowledge. So it could be that, there's some life form formed also. So we are waiting for that. And I just want to show the study I did. This is, for example, I'm doing for phosphorus. See all these lines? So what I did, this is studying, also, yes, my student also worked with together here. We formed these lines. These are, each one is a photon. So for phosphorus, okay, two or both of them the same. So we study for phosphorus, excite them, and see the photons coming out. So it is all kinds of energies here. So all this photon, each line is a photon, and they have all kinds of energies. The energies are given here. So what is the advantage of seeing that? So we know that if there's a phosphorus somewhere, it is high probability that in this energy range, we will be able to see phosphorus. Maybe not here, but in this energy range, not in this energy range, but in this energy range, there's a high probability of formation of photon line, or phosphorus line. So like here, there are dense. So another one process I'd like to mention, the line form, but not sharp line, but sharp line on a white line is called photoionization. That means, we have, say, phosphorus or any other atoms traveling, and photons are also traveling. And suddenly at the end, one electron finds, oh, there's a photon. I can absorb it and get out from this atomic system, which is called ionization. You ionize, electron has enough energy from the photon. It doesn't stay with the atom anymore. It starts to travel in the space freely. Okay, this process is very common in astronomical objects because there are lots of photons in the stars and lots of ions, plasma. So this process is very common. And so to study this, we have to study what kind of features it has so that we can predict whatever we see from the telescope, we can explain, interpret, the features. So there is an experiment in Berkeley, California. This is the laboratory. So in that laboratory, my collaborator measured this phosphorus spectrum, okay, for photoionization spectrum. But it is very difficult to understand without theory what these lines means, how did they form, how do you identify them. It's important, identification. So I collaborated with them, and so I did the theoretical calculation using quantum mechanics. So I did the spectroscopy. So I'm telling that, this feature is a little bit shifted here the way I plotted. And I'm just saying this feature, you see this coming from these ground levels, okay, coming from one certain levels of the phosphorus. You see this part is coming from here. Okay, so that's how we study. That's how we predict things. And this is the measurement, this is the theory. Okay, so what we plan to do, we do some modeling after calculating more of phosphorus. So this is like, Earth's atmosphere. So we have various levels of atmosphere. So I got this picture from the internet. So um, so the part I want to show that after, if you go from, from Earth's surface, we have various, like troposphere, tropopause, stratosphere, the ozone layer, but top one is called ionosphere, the top one. Why I'm showing it? I'm showing it because, the elements here on the Earth, sometimes, with air, they are also freely available. Sometimes they slowly surface to the upper layer, ionosphere. So if a planet, exoplanet, has phosphorus, it will ultimately go to the ionosphere. And if it is going to the ionosphere and it is passing in front of the sun, the light will go through it, and the photon, the phosphorus will be excited, and it will give out photons, which the telescope will detect. So what do we plan to do? This is our plan. This is at this time, this is the model of the atmosphere. At this time, it is Earth atmosphere because we don't know what kind of atmosphere other planets will have. So this is the Earth atmosphere. So if we have phosphorus, so we want to put our data to show where this phosphorus line will be observed. So that will be enough. So we are giving information, some prediction how if phosphorus is visible, there's a high probability some living forms are there in that planet. That means it is a habitable planet. Okay, so that is all I wanted to say. Did I take too much time? No, I think I'm okay. You can ask me question.
Ma'am, should we ask the students Here?
Yes, yes.
Okay. That's it. Anyone has any question?
Don't worry, simple question. I cannot hear.
Maybe there is no question.
Oh, there's no question? Okay, one thing I like to mention, whatever question you ask, don't think it is a simple question. Anything is fine, okay? Never feel shy to ask question. Regardless, the level, this is, something will be part of the learning process. Even though it seems like it's stupid to someone, but it is not stupid to everyone. You just become stupid for 1 second, then you know the knowledge. I think you are muted.
Yeah. Ask the question.
Hello, ma'am. So my question is, I have heard that there is a chance to study Bachelor of Arts in Astronomy. So is it true information or something wrong? And if someone pursue that field, like Bachelor of Arts in Astronomy, not Bachelor of Science, then what's the difference? And what are the countries that provide that discipline or subject?
Okay, astronomy is taught in bachelor in almost all universities in the US. Okay, astronomy is part of bachelor curriculum. So you can measure, like if you are majoring in physics or something, you can major in astronomy in your bachelor. And it is not arts, if it sometime, some university, even it's just a convention, even though you studied science, it puts the word Bachelor of Arts. I don't know why Columbia University does, but Ohio State will say Bachelor of Science, but not arts. So it doesn't matter, but you'll be studying the same material. You'll have the same major, astronomy major, like any other universities in the US. In Bangladesh, I gave a lot of books. I don't know they are being used. I know some places they're being used. Even in Chittagong University, I gave at least 20 to 30 books, astronomy books for undergraduate astronomy course. Okay, because it is it should be part of a bachelor degree curriculum. Astronomy should be taught. And I think Chittagong University is doing it right now. Dhaka University, I don't know. But I know Russia University has, Jahangirnagar University teaches astronomy. Astronomy should be taught, whether it is your major or not major, because it's part of science and physics combined together. You have to speak loud, okay? I cannot hear.
There is a sound problem and I couldn't understand your full answer. So what I understand is that you said astronomy should be taught is a part of science and physics or something. And students of science or something, if interested, then they should take it as a minor at least. But I wanted to know that if someone is interested more in the theoretical part, not in the observational part, then how should that student approach?
Well, this is the university you are studying should have that facility. But if you want to do some study on your own, there are online courses. Most of the in U.S. universities, it, it is not very easy to learn because there's no teacher, but directly that you can question. But online courses are available now, or recording at least, that you can learn if you are interested. But it depends on where you are studying, whether that institute or university has astronomy major or minor, or just a general class.
If someone takes online courses, there are free courses and there are paid courses. But if someone's major is not astronomy or related to astronomy, but they learn astronomy, then it's a part of their learning. But will it be a part of their career or something? Like, will they be able, without a degree, can they purchase their career field in that part, in that field?
Well, in the career, they want some degree, okay? And because the people who will be hiring or taking you, but astronomy department accepts students from physics, from astronomy, who major or people who are studying physics, but have some quantum mechanics knowledge, even engineering, as long as the student has physics and quantum mechanics course. So most of the astronomy department accept students from physics. But career, that depends on um, the company or the institute. They like to have people who have certification, so that they don't have to worry about it. His certification means definitely the person has studied astronomy.
Okay, ma'am. Thanks.
So, are you interested to know that some life form out there? Was it interesting? I thought, I chose this topic thinking that it may be of interest.
Interest assessment. Your interest.
Yes. Yes. I cannot hear you.
Ma'am, as you told about online free courses, so once I did a course on astrobiology, well, it was on Coursera. There I learned about the transit method and the doctor or something. I forgot the name. Anyway, so I want to know if like I have a question. I'm very curious about that. You have shown image of an alien, right? But why we always assume the shape of an alien like this, like head like this or something? I mean, how has that come, and why don't we imagine it in another way?
Yes, aliens can be different. Nowadays, if you see Star Trek uh, series or movies, they have different forms, but that's we have to symbolize something so that we recognize. That has become symbolic because of the earliest picture, in the movie, like E.T., like you have a big head and very thin hands and legs. So uh, it is possible, we that's what we thought of. So, and everyone will recognize it. That's the reason they use it. It doesn't mean it will be, because nowadays, as I told you, the movies show all kinds of aliens. There's no particular reason that we have to show that, but that as soon as someone sees that, the person knows we are talking about aliens. Okay, that's the reason. And I'm glad you studied to Coursera and you know the methods of detecting exoplanets. I did not talk about this. There are 3 radial velocity. I'm glad you know all of those. Radial velocity, transit methods, also microlensing, gravitational method. Yes. Good. I'm glad.
So ma'am, can I ask another question?
Yes.
So ma'am, search for extraterrestrial life and search for extraterrestrial intelligence. And these 2 different parts. And so if yes, then what are the differences between searching for them? Like if we search for life, then there I know that biosignature tests or something. But if it comes for intelligence, then it's not every. I mean, it's not obvious that every creature or every life form would have intelligence. So if they search for intelligence, then how do the astronomers or astrobiologists approach?
Okay. Well, all are life forms, but some life forms are able to communicate intellectually, like with a meaningful manner. So sometimes we don't understand language of, say, whale, no, or other animal, what are saying. But intelligence means we can communicate in a sophisticated, high-level manner. So that's what the intelligence, all are living form. So intelligence is also living form among them. So on our earth, we can say that human beings are not intelligence one. And other animals, they are, but not to our level. There's no, it's just how you rank the intellectual. Like we can study, we can think, we can take care of problems we are facing. Like animals will not be able to do everything, but we can. Human beings can, because we study and we have more knowledge. No? So the more knowledge we have, the more power we have to solve problems, and we have that power.
So why do we use different terms like extraterrestrial life and extraterrestrial intelligence?
As I did not quite hear you. Can you say it again?
I asked that, so why do we use 2 different terms? Like one is extraterrestrial life and another one is extraterrestrial intelligence.
Oh, we can, intelligence, I say, because we should be able to communicate. So life can be, like one cell form to animal, all kinds of things. But if it is intelligence being, that means we should be able to communicate. The signals we send, they should be consistent, not a noise. There should be pattern, consistency. So that is intelligence.
So for searching the intelligence, do we look for their signals, like if radio signals or some signals are coming? And for the life, are we looking for biosignature gases or something?
No, the 2 things, signals will be sending by them through light or some other signal, but to study, because we are not getting signals, right? So study, there could be a possibility of living form. We have to study the light coming from there. Or so because light gives our information. So light, for example, we say if you find a phosphorus photon, and we can almost assume that life form are there. So both are signals are also like photons, but it is a message. But photons are just single photon, lines, things. It is not a message.
Yeah, ma'am.
Ma'am, thank you for answering the questions of our. We will end there. Thank you so much for accepting our invitation.
I see. Okay. All right. I think our session ended, right? All right. I pray all the best to all of you who are taking this workshop. I pray that you gain knowledge and you choose, and all of you become very, very successful scientists, all of you. And who are managing, also congratulations to you. You made a lot of effort to arrange all of this. Okay. Pray all the best for all of you. Okay. Okay. Allah Hafiz. Okay. See you.